try not to.
Okay, so I mean, we'll do whatever I can do today. Who knows? I won't be my usual jovial, excited self. So if I start crying in the middle, so anyway, today we're moving into 1600, 1700. So we want to explain what was happening mathematically during that time period, but more specifically, explain how the events of this time period contributed to the development of the calculus, because now, for this time period here, we're getting into a little bit more of specifics about like how one particular subject, calculus, not general things, was invented, discovered, put together, whatever. And then mathematical figures, so I've done some work with that. I'll be working on problem sets from this area, from this time period. But again, more specifically, explain the contributions of mathematicians to the development of the calculus. Because if I ask this general question here right now, or a specific question really, is when you hear calculus, and I say, who are the mathematicians that invented calculus? What comes to your mind? Maybe your teachers have never told you. Newton, right? And one other guy. Starts with an L. It's actually where we get the notation from Leibniz. And those guys there, Newton obviously applied a lot of the concepts to physics. But then those two guys there kind of formalized the procedures and all that you study now. In fact, when we get to 1700, when we end with 1700, we can pretty definitively say, some things have been refined since then, but we can pretty definitively say that all of the procedures that you study now in your calculus sequence, those were done, those were formalized, at 1700. Some things look a little bit different here and there. But what we really want to talk about is how people like John Wallace, people like Napier, people like Ottred, Isaac Barrows, and people like that. What did they have to do with the development of calculus? And I'll share with you one of the things that Newton said later on here too. But Newton said that, because people concentrate on him so much, but one of his famous statements is, if I've seen further than other people, it's only because I've been standing on the shoulders of giants. So he certainly acknowledged the people in the past that he stealing from or building on. That people can only, they say, and I'm not sure if I've shared this before, but they say that your creativity as a mathematician usually ends by the time you're 30. I'd probably say even younger now, because we corrupt you with formal education. And we get you to just think about these procedures and doing things this way, and we don't let you have creativity in problem solving. Didn't have as much problem back then because of the formal education that we have now, and everybody wasn't geared. There was no PSSA test in 1648. There was no PA. But anyway, the point there is that we corrupt people, but then your mathematical or your mind's development is the creativity is kind of stopped at age 30, and then that's when, from a historical standpoint, people go into teaching, because okay, now I'll just share my knowledge. From then on, before then, it's research. After that, it's more of sharing my knowledge with other people. But it's interesting to hear him say that, because there's also a statement from a 18th century English poet who said this. He said, this is the high regard that we hold Newton in. All right, in one of his poetry, Alexander Pope is his name, just an English poet, and one of his sayings is, nature and nature's laws lay hidden in the night. God said, let Newton be, and all was light. Guys just wanted his, poetry. That's probably holding somebody in a little too much high regard, but you get the point, right? Newton is the one who gave us, a lot of his understanding and of nature's laws, physical laws and stuff like that. Nature and nature's laws lay hidden in the night. And then God said, "Let Newton be," and all was light. It's interesting to think about that. But anyway, so we're going to work on that. I'll probably sit down a lot today, so I'm sorry it's going to be boring. And this is an unfortunate day that I need to talk on it because you just finished your test and paper. So I've given you all your papers. Yeah, when I sent you your grade, I forgot to send the papers, so I did that yesterday. Luckily, actually, it was John that reminded me because he was late and sent his papers. So when you sent your papers, I was like, when I was returning them to you, I was like, oh wait, I didn't actually return them to everybody else. Here's Kate. So let's see.
Yeah,
I pretty much correct everybody's stuff. There's not that many people in here to not be able to do that. Anything I want to say specifically? Number 18. You do just have to make sure when you got to 7 plus 8, just checking the two add-ins, the 3751 and the 287. So when you got 7 and 8, you added those up, you got 15. You can't stop there. You can't say that 15, now I guess technically you could say that 15 doesn't equal the 14 from before, and of course that's kind of the same thing as adding 1 and 5 again and getting 6, and adding 1 and 4 again and getting 5. There's not, I kind of already went over 21 there, nothing really I want to say that. I corrected everybody's stuff. Any questions on any of those? 17? Yeah, now 17, if you need to be reminded of that, I obviously could have used the problem, but I told you where to start, and then when you go up here to 2, it has to go down there. When you go up here to 3, it has to go back here. And you can't go diagonal, so you drop it down. Then you go diagonal. I think that was where some people messed up.
Yeah,
I think you actually went over here, didn't you?
Yeah, I went up and then down.
Oh, yeah. Went up and down like that. That's how you went over there. I assumed you said, okay, I can't go that way, I'll go that way instead of that way. But yeah, if you can't go diagonal, then you drop it down. Then you go up and up. And since you can't go diagonal here, because that's an empty box, even if you printed like it was a box, where are you going to go down here? There's nothing there. So you can't go there, so you drop it down. Then when you go up here to the side of that, back over. Hopefully you do see that algorithm that many of you call the lattice, which I think was Alex. Did you say something about the lattice method saved your butt many times?
Oh, yeah.
He made a comment. It's funny because some of you said you've never seen it, and his comment was, this has saved my butt many times in math classes. So if we didn't know how to do that, but hopefully you see that if you were to actually set 4327 times 285 in your standard algorithm, you see where it is all the same, right? All you do when you multiply 4327 times 285 underneath, you're just multiplying 5 times everything, you're multiplying 8 times everything, and you're multiplying 2 times everything. That's all you're doing. The question is just where do you put it, right? That's the only question, where do you put it? This has a nice place to put it. I don't know that, when we do this right here, when we do, the only problem there is, it's difficult to get, parents and anybody necessary, older teachers or whatever, to buy into the fact that it is just an algorithm. When I say 5 times 7 is 35, and I put that right there, you ask most people, why do you do that? I mean, they're not going to be able to answer it. And then if I were to do all of the work, now this is an easy one because it's the very first one, but if I were to do all of the work and we could get my 3 lines and then add them up, and then step back and say this, in fact, 5 times 7, and step back and said this, where is 35? Now, I would hope that most people could answer that because it's the very first one, 3 and 5, right? But now think about it. 200 times 20, okay? So 200 times 20, 4,000, right? 200 times 20 is 4,000, that's what that would be. You're gonna have a 4 in here, maybe 0, 0, whatever. But the question, if you ask somebody, where is the 4,000 at? They might have a hard time finding it. Because actually, what would you have? You'd have 2 zeros and a 4 there. Is that right? You have 2, 1, 0, 0, 4, 2 zeros and 4. Trying to think what it is. But the point is trying to find that maybe that's not because it's 2 times 2. I'd probably rather do this 8 times 2 because then you have 16, right? So you have 16, but really it's 80 times 20, so it's 1,600. So you're going to have a 1 up here, a 6 down here, and then 2 zeros someplace. The question is, where is the 1,600? You're still going to have a hard time answering that. Whereas over here, if you look at this algorithm here, when you have 8 times 2 and you have 16 here, if you understand this is the ones and the tens and the hundreds and the thousands, then you can see this is 1,600. I mean, these right here are added on to other things, but you can see the 1,600. It's just a difference in organizing the partial products. It's not that big of a deal. Except to understand it. Okay. So the way I have this time period broken down is, like I said, forgive me for the way I learned this stuff. Himself, so I'm going to split this up, this time period up into an overview and then specific mathematician. Now, most of the mathematicians I am referencing in the overview, I've given some detail on what they did, but it is more of an overview of the time period. In the other PowerPoint, then I'm actually going to have you kind of look at on your own, and that way I don't have to go over in detail for homework. It gives a little bit more specifics about the certain people, and some of them are because history, right? We're only a few hundred years from now. From this time period here. We're only a few hundred years from this time period, so historical records are much better. So we know a lot more about these people in general. Sometimes Diophantus, when the heck was he? I'm not sure. Archimedes, we have a few things, the legends that may or may not be, but we know pretty definitively about the stuff that happened in 1600, 1700. A lot of good records there, and some I enjoyed looking at some cute little anecdotes about the different mathematicians. Like for instance, Isaac Barrow, who nobody remembers him, but he was Isaac Newton's teacher. Okay, and the teacher's always important, right? Nobody ever remembers the teacher. Everybody always remembers a famous person. No, and so Isaac Barrow, he was a troubled youth. Okay, his parents hated him. And his dad was found to be praying one time, and he was praying to God, and he said, if you need to take any of my kids, I could best spare Isaac. He was just a troubled boy. I mean, imagine some of the parents said no. I'm sure my parents said that to me when I was young. Interesting little anecdote there. Newton was like the absent-minded professor. Okay, and there are stories about him where one time he had some people over for dinner, and he excused himself to go get a bottle of wine, I think it was, and he never came back. He went upstairs, got working on a problem, got distracted, and forgot what he was doing. He ended up going and getting his church clothes on, and he went to church. And people are in his house. Okay? Other stories about that, of the other people. So, interesting. Newton also had some mental problems too, but most math people do. So you'll get there too if you're not already crazy. Problems that just drive you nuts. So, think about the 17th century. I alluded to this a little bit on Thursday when we kind of started out. This is the time where we're starting to get machines and inventions, and this is really where calculus kind of got stuck, because it was once the calculus got kind of invented or whatever, it got stuck because Newton and his contemporaries were just applying it to physics rather than developing it as some cohesive system of procedures and theorems and things like that. They were so concerned with using it to describe physical phenomena. Not a bad thing. It was just that was the times. The times was so. If you think about it, people are starting to do stuff. There's a lot more people working on things. And what happens when you get a lot more people working on things, right? Things are invented. This is the time where pumps and hoisting machines and firearms, printing, windmills, clocks, etc. Were being invented. Then this is also a time. So at 1600, and you kind of have to put this in perspective. You'll read a lot on the mathematicians that did a lot of their writing on religious aspects as well. So for instance, Rene Descartes, which we know as what do we know? What do we know about him? Somewhere you should have. Descartes, the Cartesian something. What do we get from his name? Cartesian coordinate system, the XY. We plot things because of his development of analytic geometry. We'll talk a little more about that, but analytic geometry. Analytic geometry just takes, instead of taking geometry like Euclid did and going from axioms and building up to theorems, analytic geometry turns a geometry problem into an algebra problem. Okay, so think about a parallelogram. How do you prove something's a parallelogram in what we call synthetic geometry? I mean, you got to prove that, whatever your definition of parallelogram is, then opposite sides are parallel, right? And how do you normally do that? Well, you look at the angles, right? If these angles are supplementary, then those things are parallel, and then you get to something like that. Well, analytic geometry takes a parallelogram, puts points on it, and puts it on the Cartesian coordinate system. Okay? So we have all this regard for Rene Descartes. But in his writings, know that there are 32, 31 diagrams, and never is there a diagram of the Cartesian coordinate system. Okay? It took a while to develop that. Never is that. And also, the only thing he ever wrote on math is an appendix to a book. Now, it was a 100-page appendix. Usually you think of appendices as a couple pages. It was a 100-page appendix. It was his appendix to his most famous book, which I can't remember the whole name. We call it Discourse on Methods, but it was Discourse on Methods for rightly proving, basically physical phenomena, or whatever. It was his religious text. Okay, it was a religious document to him. That's where we get, everybody's heard of, I think, therefore I am, right? That's how you prove that you exist. I think, therefore I am. That's the thinking. How do you actually know you're here? Well, I think, therefore I'm here. I'm a rational person. I think I'm here, so therefore I am here. But anyway, that's in his book there. But it was a religious text, and then he just wrote one appendix on that. But everybody, even Newton, Newton went back and forth between religious writings and that, because think about what's happening here. What in your world history, whatever classes that you've taken, what was happening in the 1500s? So right before this, as far as religion goes. Nobody knows what we just started, or we just celebrated 500 years of last October. So it would be 1517. I know they don't teach you this stuff in the history what we call the Protestant Reformation. Okay, so that was when Martin Luther, not Martin Luther King, Martin Luther, a Catholic monk, nailed his 95 Theses to the walls, or to the church door in Germany, and basically was calling out the Catholic Church on some of their teachings. Okay, now why was he doing this? Because before that time, the general person wasn't reading the Bible. The church was reading it and interpreting it for you and saying this is what it says. Well, then the printing press, right? It was the printing press. So when the printing press was invented, then the Bible was starting to be printed in what language? Latin. Okay, the Bible was printed in Latin, and the common people were reading it. And then they said, and Luther was like, wait a second, the Catholic Church been telling me this, and that's not what the Bible says. And so he called them out on it. And then now you have your, distinction between Catholics and Protestants, and so a lot of religious fighting there. Now, not like Hypatia, fighting. For those of you, they were clubbing each other to death and people through it. It was much more rational thought, after the Renaissance. So, and the Crusades are done, right? The Crusades 1200 and that. So, those are done. So we're at least arguing through, the town square and articles written and things like that. But anyway, the point is though that most people who were intelligent at that time were writing on religious orders too. So the Catholic Church was trying to defend their teachings, and the Protestants are trying to say, no, you're wrong. So that's kind of the first thing there. A lot of things happening in the 17th century with respect to things being invented, and so of course, let's explain things through mathematics. And that is something interesting to think about. Do you need mathematics to build a windmill? I often think about this sometimes too. Do you need mathematics to build a windmill? Well, you probably don't need the mathematics that you can use to explain the operation of the windmill later on. You know what I'm saying? Just build a stinking windmill. So who needs that? So that's what the engineer does. That's why there's a difference between, and like math departments at a university don't usually like to hire engineers to come teach in their math, because they're going to be all about the practicality of things, and they don't care about the proofs and the rigor and stuff like that. They just build it. I need a machine to do this, just build it. And then it's mathematicians that come later on and say, okay, well, let's use mathematics to explain how, this stuff works. I mean, both are good. It's not one better than the other, but do I need, to know all the mathematics before I can? It's like with the paintings, right? You ever seen Escher paintings and stuff like that? Escher, the MC Escher, the artist that makes things look like they're going nowhere, like a waterfall, and it makes it look like it's not going anywhere. You ever seen those? What the heck, man? What's education doing? Come on. Have a better education system. Heck, we learned some stuff here.
Oh, yeah, I've seen this.
That's right. Oh, can you get a bigger picture here? This is, I like waterfall. That's waterfall's my favorite. Where? Come on, give me waterfall. Give me bigger.
Yeah, I've seen that.
So there's clearly a waterfall, right? But follow it. The water's flowing uphill, right? Now there's some mathematics involved there with perspective and stuff like that. Escher know anything about mathematics? Probably not. He was a painter. Now you're intrigued by that, aren't you? This right here, what's that? Drawing hands. That one's drawing that one, and that one's drawing the other one, right? These are just some of his paintings that he did. But anyway, my point is that we don't necessarily need to think about the mathematics that's involved in order to build a machine. Usually that comes kind of after. But anyway, the second thing is This is also the time of revolutions in astronomy. Okay, so we tend to know Copernicus and Kepler and even Galileo a little bit better than this guy here, Tycho Brahe. But Tycho Brahe is actually Kepler's teacher, who Kepler came up with the 3 laws of planetary motion, and he basically just took Tycho Brahe's data. Tycho Brahe spent his life just collecting data, and then, you know, he's not going to live forever. He dies, and Kepler inherits his data, and then he makes sense of the data from a mathematical perspective. And this is what happens in mathematics all the time. You know, some people do something at this point in life, and then, you know, they die. They leave papers, and people who know them or going through their papers say, "Oh, what can I make sense of this?" And that's a probably good perspective, because you think about all the people who have been, you know, good mathematicians that probably have died, left a bunch of work, and nobody's ever going to see it, right? Their grandkids and kids just burn it. You don't care about that, right? Anyway, they're really trying to figure out man's place in the universe. You know, using man's power, rationalistic thinking, to explain the phenomena of astronomy in some rationalistic way. So gone, you know, as we go west, we get more rational. We've talked about that before, right? We get more rational as we go west. East still, even today, sometimes has a little bit more mysticism to it. And here we're trying to get, you know, make a case for more rationalistic thought. Kepler may have something to do with physics, even though we don't think about him, or physics, calculus, even though we don't think of him as being one of the big, you know, people who did anything with physics, because he evaluated volumes of solids just for their own sake. And what did he do? He rotated segments of conic sections about an axis in their plane. Isn't that what you're doing in Calc 2 right now, right? You take up a curve, and I know you don't look at them as parts of a conic section, but if you rotate y equals x squared plus 4, okay, around the x-axis, you're rotating a part of a conic section. You understand what I'm saying there? You know, from 0 to 5 or whatever, and you get that horn shape kind of a thing. That should be all stuff you're doing now, right? Calc 2. Ring a bell. You're like, what? What are you doing in Calc 2 now? What are you doing in Calc 2? What are you doing? What are you doing? Log? Just logs. What section is, or what chapter? You know?
6. We just got in.
Yeah, maybe 7 is application of integration more. So you do you solve the revolution and then later. So when you think about that, you know, all you're doing is conic sections. And then Galileo, you know, we know him, right? You know, he stuck with the Copernicus system of the universe and got, you know, banished from the church because of it. But for him, we owe mechanics of freely falling bodies. He is the one who kind of put together experiment and theory. So he did a lot of experiments and then tried to rationalize them by looking at the mathematics involved in them. So he was one that we owe, you know, kind of intensive use of mathematics. Again, calculus, Galileo, well, yeah, he studied a lot of motion, relationship between distance, velocity, and acceleration, but they did it in very rudimentary ways that we'll find when we do look at some problems. They did it in very rudimentary ways, and they don't look like anything that we do today. So for instance, one of the methods that comes out of this time period from some people is, if I have this curve and I want to find the tangent right there, what I do is I construct a circle. So this is very geometric. I construct a circle with the center somewhere on, I gotta get my center right, but my center on the x-axis, okay? And then from there, I use my geometric constructions to get a radius. And then if I make a if you remember this from geometry, I know you haven't had geometry here yet, but if you do remember this from geometry in high school, if you have a radius, and if you make a perpendicular line, then that perpendicular line is tangent to the circle, which then also means it's tangent to that curve. Now, we don't do it that way. You know, we take, what's the curve? You know, it's y equals whatever, x to the 4th minus 3x cubed. And we find the derivative, and then we got these fancy ways to find the derivative. So that's why we don't really spend much time, any time, in a calculus class talking about how Galileo used to do it. You always hear Newton, you hear his notations and so on and so forth. So, a couple of his pupils were Torricelli and Cavalieri. We're going to do Cavalieri next and see Cavalieri had a really great principle that leads to pretty much what we do now with integration. So, and then Galileo, even back then, while we didn't think a whole lot about infinity then, here's one of his quotes or one of his sayings. Think about this. You won't think too much about this until number theory, but just to think about what he said concerning infinity. He said, neither is the number of squares less than the totality of all numbers. Understand what he's saying? So the number of squares is not less than the totality of all numbers. So when you think of the squares, think about the squares. The 1, the 4, the 9, the 16, right? Those squares. And then think about all numbers. Doesn't it seem to make sense to our mind there would be less squares than there would be numbers? I mean, you're skipping numbers to get to the next square, aren't you? You're skipping several numbers. But he is saying that neither is the number of squares less than it, nor the latter greater than the former. So neither is there more of these than there are of those. So there's not less squares, and there's not greater whole numbers. That's a little bit non-intuitive to us if you think about that, isn't it? I mean, you'd think that there'd be more numbers than there are squares. But remember, there's no end to the numbers. So that kind of gives us a little bit of thinking on his idea of infinity. So in his case here, he was saying both of them have, he didn't use these words here, and these are words that you'll use in number theory class and that, but he might have said the cardinality, so the number of them both, the cardinality would be the same. He would say that. Now again, you'll think about that later in your number theory class. So then, along with him, now we're talking about, now we're talking about getting a little bit more systematic with what we call calculus, okay, because I don't know what you're walking out of calculus with. Excuse me. But when you think about calculus, I hope you're thinking about infinitesimal changes. Okay, really, really small changes. Think about this. Go back to Calc 1. And one of the things you did a lot of in Calc 1 was to find the maximum of a function. Right? The maximum of a function. Now, when I look at this point here and this point here, when I look at this point here and this point here, I can say two things about this, right? I can say the x value changes, and I can say the y value changes, right? As I get up to this point that I'm going to call the maximum, and if I get right there, the x value certainly changes, right? The x value certainly changes. And the y value changes, ever so slightly, right? It does change. But as I get close, and let the x value, or let the x change, the delta x be 0, right? Let that be 0. As that gets changed, I'm looking for as that gets close to 0, I'm looking for the point where there is what kind of a difference between the y's. If I get the absolute max up there, if this goes to 0, then the y value, there's a little bit of change here. If I get close, there's just a little bit of change. There's a little bit of change, right? But if I get to that point right there, what kind of change is there? None. What?
Oh,
Well, there's no change. What'd you say?
But even from when you keep going.
Well, yeah, but if I keep going,
That's
then I
what you
start
said.
falling, right? Yeah, but at that point right there, as this gets to be 0, the change in the y is 0. Isn't this how you find the maximum? Right? That's how you find the maximum. right? You set the derivative equal to 0, and you can find the max or the min, because you're looking for where the slope of the tangent line is 0, right? This is not a maximum or minimum point. Why? Because the slope is not 0. This is a maximum or minimum point because the slope is 0, right? You just actually learned that for the first time, didn't you? Oh, my job is so hard. So Cavalieri has a couple of principles here, okay? Here's what he did. And this is an interesting principle to look at. So he said this. He said two solids. Oh, wait, let me see what I said. Oh, well, actually, what his thinking was is this. He was one of the first to start thinking about how a curve is actually obtained. And if you think about this, this should help make calculus come to life a little bit. He said that a line or a curve is generated by a point that goes on it. Okay, now think about what that means. If this curve here, how is this curve here generated? I know what we do. We just graph. Oh, and sometimes we plot points, and then we get a smooth curve, right? But understand what he is saying. His thought was this. His thought was, I'm going to look at this line, or this curve, as being formed, being generated by one point that just keeps rolling. Infinite number of points, maybe. Okay? But it just keeps, it's one point that just keeps going, which means this. It's rolling along, it's rolling along, it's rolling along, but think about it. That means that any one time, it's moving at a certain speed, right? A velocity. So at any one time, it has an instantaneous velocity. Also known as starts with D, and it's very prominent in Calc 1, and derivative, right? So the instantaneous velocity, the derivative of a function. The instantaneous velocity. So anyway, his principle said this though. He said, if you have two solids, and I said this before, but integration came before differentiation, and this was kind of the leading thought here, is Cavalier's principle says this: two solids of equal altitudes. So I have some pictures up here, but just think about two solids. If you have two different solids and they're the same height, so equal altitudes, they have the same volume. They don't have to look the same, but they do have the same volume if plane cross-sectionals. So if this is my solid, a cross-sectional is when this plane cuts this, in this case a circle, right? It would make a circle. If all of the plane cross-sectionals at equal height have the same area, so if this was a solid, and we'll just pretend here, if this was a solid and this was a solid, they were the same height. And if you cut a plane here, and it cut this, and then that, and that area was equal to that area, and everywhere else, that area was equal to that area, and they were the same height, then doesn't matter what they look like, they would have the same volume. That makes sense, right? You cut it up into an infinite number of little pieces. Makes sense. And that allowed him to actually perform what we would say is the equivalent of integration of polynomials. Because look, think about it. There's a picture and there's a picture. They have the same volume, right? They don't look alike. But why? You see the principle? Same height, okay? Same height. And cross-sectional areas are the same. Okay? And then if you kind of turn your head, you can kind of see a polynomial there if I let this be the x-axis. But that would allow you to do what you do here, right? And perform integration. Other pictures though, just think about it. These two triangles, same area. How do I know the same area? Well, same height, okay? And same base, so I guess I could say this, right? Area is 1/2 base times height of any triangle, right? If they're the same height there, and as long as, my assumption is that those bases are the same, and if those bases are the same, then area equals 1/2 base times height is the same for both of these triangles. But as you would pull this point parallel to it, then that distance right there and that distance right there would be the same. So now, this isn't about volume, that's about area, so the same thing is with area. Same thing here, right? These two figures would have the same volume. All you did was slide it over, right? But the cross-sectional areas are going to be the same. And even here, I mean, that's just a corner representation. But here, you have a pyramid and a prism, right? But as long as that is equal to that in area and that's equal to that, the volumes are going to be the same. That's Cavalieri's principle. All right, third main thing in the overview. Gradual evolution of calculus was considerably stimulated by the publication of René Descartes' Geometry. Again, that wasn't a separate book. It was just an appendix to a greater volume. And that brought the whole field of classical geometry within the scope of algebraists. So you have algebra, and there's some good stories about René Descartes. One of the legends is that he was very sick as a child, which that's true. And so he used to just lay in bed until like 10 or 11 o'clock. Some of you guys are like that. Till 10 or 11 o'clock. And while he was up there one time, he was contemplating the movement of a fly or something on the wall, and he was describing, or on the ceiling, and he was describing it by the distance away from the, if it's right here, the distance away from here versus the distance away from here, and there pops out the coordinate axis system. It's a good story. I don't know if it's true or not, but anyway. But when you study calculus, your calculus book isn't called that, but a lot of calculus books are called calculus with analytic geometry, just because you're not doing the geometry that you did in high school or our geometry class here. You're putting figures on a coordinate axis system, and then you're analyzing that aspect. So that is what is meant by coordinate axes. And it took a while for people to accept negative values for coordinates. We don't think much about it right now, but I'm pretty sure we'll remain. Fourth thing on the 17th century overview. Cavalieri's book stimulated a considerable number of mathematicians in different countries to study problems involving infinitesimals, because now, remember, how are other countries, or how are other people finding out about some of the publications of that? The printing press, right? The printing press is making things be much more accessible. You're starting to have some journals at this time, some publications. Before this time, there were no writing back and forth. People are still writing letters to each other, but for the mathematics. But a lot of times, it's being also starting to be published in journals. The tangent problem started to take a more prominent role beside the volume problem. But remember, calculus all started with volumes, because even Archimedes was trying to figure out volumes and areas, and he was cutting things up into infinitesimals and making little small cuts rather than worrying about the tangent problem. But now the tangent problem, because now, why the tangent problem? Instantaneous velocity, okay? Because now Newton is worried about physics, and he's trying to use this new calculus to describe physical phenomenon, and so he can do that based on velocity and acceleration and things like that. So, and that's the tangent problem. Geometry, you've still got this fight though. So don't think like today. Don't get your mind in today's thing. Today's thinking is we pretty much just automatically combine algebra and geometry until we look at geometry from a high school standpoint or a college standpoint, and we just do it as an axiomatic system. But back then, though, there were people who were only geometricians and only algebraists, and so people looked at things in different ways, which is still partly true today. Mathematicians today will look and somebody will approach it from a geometric standpoint. Somebody else will approach a problem from an algebraic standpoint, and usually one helps inform the other. So geometric approach, Torricelli, Barrow, and who was Newton's teacher, and Christian Huygens. Those taking algebraic approach were Fermat, Descartes, and John Wallis. We tend to hear more about Fermat and Descartes than Torricelli, Barrow, and Huygens, because we take things from an algebraic approach. So a lot of ours stuff and methods goes back to Fermat and then Descartes as well. So Fermat discovered in 1638 kind of this method right here, and I'm going to do a couple problems with it later on. A method to find the maximum and minima, which think about what he just did. He did exactly what I did up there. He slightly changed the variable in a simple algebraic equation and then let that change disappear. And that's what you do, whether the connection was made or not, that's what you do when you let delta x go to 0 in your limit definition and all that. I know you get caught up with procedures and that in your calc classes. And then there were determinations of tangents and areas, but the relationship between the two, and hopefully you get the relationship between the two, was not discovered until Isaac Barrow, which we call the fundamental theorem of calculus, right? So we have integration, you know, and I hope you have made this connection at some point here in the last 2 semesters. You know, you spent a lot of time last year having an f of x and seeing how that led to an f prime in x. And then, you know, this year in Calc 2, you are spending a lot of time, and this isn't necessary, well, if you think about it, it is. When you find the integral of a function, you're finding the integral of something, but that function is actually the derivative, right? And you are trying to find the function, correct? And of course you have to plus c if it's an indefinite interval. But the point is, if today we should know this, but this is our fundamental theorem of calculus that you use, that you are constantly using in Calc 2, right? The integral from a to b of f of x dx is equal to capital F of b minus capital F of a. That look familiar? That's what you do, right? You find the antiderivative, and then you put b in, and you put a in, and then you subtract the two. That looks familiar, right? Makes sense? But think about what this is saying. You know, you're really saying here what? You're really saying that f of I'll say f of x here. You're really saying that the derivative of f of x. You're really saying that the derivative of capital F of x is equal to the f of x. You're finding an antiderivative, right? But that right there is if you think about it, it's a pretty crazy discovery because, I mean, derivative, you're finding the tangent line, and then the area you're finding, or the integral, you're finding the area. How the heck are these two things related? And hopefully your calc professor has done a good job of explaining how they're related. And then there was just a lot, when Barrow found that, just a lot of activity, a lot of correspondence between mathematicians, and hey, let's figure this thing out, let's exploit this relationship, and pretty much that's why by the end of 1700 you have your undergraduate calc curriculum pretty well established. Fifth thing is, men like John Wallis, Christian Huygens, they continued to develop ideas of the calculus. They wrote the most advanced form before Newton and Leibniz. Those are the traditional founders of the calculus that we study today. Another thing, lots of different fields in this time period were being developed. Fermat studied Diophantus, and then Fermat and Pascal had some really good correspondence letters in 1654, I think it was, and with that they founded mathematical theory of probability. And why did they do that? Because this is the time period where insurance is being developed. Okay, so this is kind of the start of actuarial science as well. So insurance is starting to be developed, and then also noblemen were asking them about how to win at gambling. And so if you think about it, mathematical probability is a strange thing because mathematics is so rigorous, right? It has to be precise. So think about this. Mathematicians have found a way to make something that is pure chance an exact science. Think about what I just said, right? The theory of probability is, I don't even know if I can say that. The theory of probability is saying that we're going to take something that is pure chance and make it, mathematically rigorous. What were you gonna say, Gary?
Can you count cards?
No. I mean, that takes a mind that is, you know, very advanced, I guess. I mean, I could probably figure, and I'm not a gambler or anything like that, so I don't study any kind of cards, games and that, but, you know, when I think about that, and I've heard other people do it, like, I could probably do a good job of it, you know, by writing stuff down, you know, the people who do it in their heads, holy smokes.
My one high school stats.
Good.
Count cards.
Yeah.
He was like, he was telling us, he tried to teach us if we had time, but
Yeah.
we didn't have time.
Yeah, I mean, you know, I guess, sometimes my problem with, you know, even just card games. I play card games. Big into card games. You know, yeah, you can talk about probability and that, and yes, that in itself is an exact science. But when it comes down to playing cards, you're also at the mercy of how somebody else is playing as well. You know what I'm saying? So you're at the mercy of how someone else is playing. And also, obviously, you know, what cards you were initially dealt. You know, I mean, you could be dealt a hand where you know exactly what to do, but if the person on my right was immediately dealt a full house, you know, I'm probably going to lose, you know, right there. So, but anyway, yeah. So people were asking, you know, like how to win it. So they actually came up with the theory of probabilities. And then Pascal, we know him for inventing a computing machine, probably the first computing machine. His dad was an accountant, and to help him add, just an adding machine. Okay, it looks like this. It looks like that. It was just an adding machine. You'd set the levers at a certain place, and then crank something, and it would come up with the addition of. You know, now we would never use anything like that because we could add, or have a calculator, but. So and then he also wrote on the arithmetical triangle. I mean, he didn't call it Pascal's triangle. And somebody wrote a paper on that was really, he wasn't the inventor of it. Who was that? Was it you?
Yeah, we got some China.
But China, yeah, it's ancient from Chinese. But we call it Pascal's triangle just because so much of our history comes from Europe. And he was really the one that, you know, wrote on it. But and then, you know, understand what happens too, is we have his writings, and then we've been talking about him for 300 years, Pascal's triangle, Pascal's triangle, Pascal's triangle, and then all of a sudden somebody realizes, they unearth something that says, oh, Pascal's triangle was known, you know, 2,000 years before Pascal. Well, we're not going to change the name all of a sudden to, you know, whatever. It's just like imaginary numbers, you know. Imaginary numbers, that's the stupidest name for any number, right? Because, I mean, it really is real, except it's not a real number. Okay, but I mean, it really is real. But you're never going to get the whole world to stop calling them imaginary numbers. It's just too steeped in, you know, history. But anyway, and he was the first to establish the principle of mathematical induction, which you should be looking at in 2005 something here. But yeah, I mean, good study for some people when it comes to writing your essay paper here. You know, maybe you want to do something on all of the patterns and what good the Pascal's triangle is. I mean, any one of these things we could pick apart for one class period. But you know, if you don't have time for that, so you can do some of your outside research on that. And then the seventh thing here for 17th century, a general method of differentiation and integration derived in the full understanding of how one process is the inverse of another was not going to be discovered until men mastered both the geometrical and algebraic approach. So understand why it was kind of in a little bit of a lull there, is that it's not going to be invented until, like, because remember, the group over here was looking at it from a geometrical standpoint, the group over here is looking for looking at it from an algebraic standpoint. The only people who are going to come up with the real, you know, what we study today is going to be somebody who understands the geometrical and algebraic methods. So fortunately or unfortunately for you guys, you need to understand both geometry and algebra to really understand the calculus, okay? And really that means that those people could only appear after about 1660, when both algebra and geometry had kind of been established sort of the way we look at it today. And they did appear in these guys here, Newton and Leibniz. And as far as they go, you know, there's some speculation, and this really tore England and well, England and Europe, but really Germany. So Newton's from England and Leibniz is from Germany, and those two countries just didn't talk for the longest time because of calculus. Okay, because Newton came up with his ideas first, but Leibniz published them first. And you'll see some of the things on Newton. Newton did not like criticism, so he published a couple things on optics, and then people really like slammed him, and then he said, "I'm not going to publish anything else." So he didn't publish anything. And then Leibniz, who they kind of figure they probably did independently discover it. Nobody thinks Leibniz really stole from Newton. They probably did independently discover it, but Leibniz actually got his work out like 15 years, 20 years before Newton, even though probably Newton had it like 10 years prior to him. So it's kind of interesting on there. You're really thinking about it. So I mean, that's an overview of. Tiny bit. And I'll just go through some of these things in our time remaining here, and really what I want you guys to do is kind of pick apart these slides on the mathematicians, and you'll kind of consider them in some. Eventually, obviously, you'll be writing something, delving into one thing yourself from this time period, and maybe this will give you some ideas and that. But I have this broken up into 3 different parts. The first part is what we call the dawn of modern mathematics. Like, now, even though it's 1600, 1700, remember what I said before, that at the end of the 1700s, pretty much we're done. We can't really go on much further talking about some of the in-depth details of what was developed, because after that you get into such specialization that just as sophomores, as undergrads, you can't. You need to know more number theory and modern algebra and stuff like that. So there's a difference between taking a history of math class as a sophomore, as a senior, unless you've had all that stuff, and then as a grad student or whatever. So I try to just stay true to, even though Calc 1, that's it. So we kind of can't really go on too much further than that. But so the dawn of modern mathematics, like what led to this discovery of calculus? First guy, John Napier. Some of you might want to, and I'll do a couple problems on him. But you remember John Napier from before? He was the inventor of what? Start with an L. You're doing it in Calc 2.
Logarithms.
Logarithms, right? So John Napier invented logarithms, and he was an interesting character. All right, I'll get to logarithms in a second, though. But he was violently anti-Catholic, but that goes back to the Protestant Reformation time period. He championed the cause of John Knox, who is the founder of the Presbyterian Church. So there's a Presbyterian Church. John Knox, right? And then King James the First, ring a bell? King James Bible, right? That was the main English Bible for years. King James, like 1611. So violently anti-Catholic, and that would be the Protestant Bible. That was like the first Protestant Bible. So if you're Catholic and you have your books of, help me out, Apocrypha? What are they? In the middle of the New Testament, Old Testament. No Catholics here that know that. Books of the Apocrypha.
The apostles?
No, I mean, some of them were apostles. They're just not the books of the New Testament. So you have the Old Testament, New Testament, and the Catholics, the book of the Apocrypha, like Maccabees 1, Maccabees 2, and those are in the Protestant Bible for various reasons. But anyway, it's interesting here. He wrote prophetically that sometime in the future, now think about this is the 1600s, right? Sometime in the future there would be pieces, they're inventing things, right? They're inventing things. Sometime in the future there are going to be pieces of artillery out there that are going to look like this. Like he described what they would look like, and it came, to fruition later on that, you can look back and see his description. Looks like the machine gun, looks like the submarine, and looks like the army tank. So it's kind of interesting to think that he envisioned that there would be some underwater, ship that would be able to sneak up on, other, whether it be a coast or other ships and something like that. It's just a submarine. Kind of interesting there. Now remember, they were trying to get ways to make computations easier. Now, we would never do this today, but I'll show you an example here. The invention of logarithms did just that. So for them, the power of logarithms was as a computing device. What is it that we do with logarithms now? You may know? What do we do besides frustrating things and calculus? But what is it? Our power of logarithms that we usually think about in the solution of equation comes from, if we say something like this, well, I'll put it easy here. What's x? Clearly x is 2, right? Clearly x is 2. I don't know, right? I mean, I can guess. It's more than 2, but it's less than 3, and it's closer to 3 than it is 2, right? I can do that. So I can, say something like 2.7 or whatever, check with my calculator or whatever. But we do this. We, you gotta think about what you've been doing in math for the last, how old are you? For the last 20 years or so, okay? Think about what you've been doing for the last 20 years of your life. Well, probably not quite 20 years. You've been trying to solve for x, right? What? We'll have a competition to see who's older. But you've been doing things like this. You've been trying to solve for x, right? And 2x plus 4 equals 7. And then somebody did this, right? You say, oh, I can do that, right? And then somebody did this. Oh, put out the value, do all sorts of things, right? What if it's the square root of that? Think about it. That's what you've been doing, right? You've been trying to figure out how to solve the methods for solving all these various types of equations. The last thing that you probably should have done, like in a pre-calc class, is put the variable in the exponent. Okay? Put the variable in the exponent. How do you solve that? What would we do? Take the log of both sides, right? So we'd say log 3 to the x equals a log 21. And then we do what? Properties of log, what we do?
Bring the x down.
Right, so we'd say x log 3 equals log 21. Then we divide by that and pull out our calculators, right? Now, before calculators, there was just a big old fat table of logarithms. And then you could solve that. But for these guys, for Napier, they didn't have our standard algorithms of multiplying. So when they did this, but they were really good at making tables, remember, right? People were really good at making tables. When they wanted to multiply something like 3, and this is an easy example, but 3.2 times 4.8, and we would know that as 15.36, okay? Now, but again, we would never use logarithms this way, okay? We'd never use logarithms. You can check this on your calculator. But 3.2 times 4.8 is 15.36. What logarithms allowed you to do is pretty cool, because what logarithms allowed you to do was to turn a multiplication problem, which is difficult, not for us, but you'll go to 1600, and take a multiplication problem, which is difficult, and turn it into an addition problem. Now, how the heck do logarithms do that? Well, there might be a hint to that because you know this rule, right? What are your properties of logarithms? The log of AB is equal to what? Log A plus log B, right? So log A plus log B. So there's some connection between, right? I don't know what it is, but there's some connection between multiplication and addition. We don't talk about it when you're doing that stuff. It's just like that's a property. You use it to solve those equations that I did, and now move on with your life. Okay? But I want you to think about something here. If we were to do this, if we were to find the log of 3.2, now we'd have to do it with our calculators, but they just spend an enormous amount of time making tables. if I took the log 3.2, because they didn't have algorithms yet, and made it, and it's about 0.505, whatever, and find the log of 4.8, and that gives me 0.6861, something like that. And then I added them together, okay? So if I add those together, I get 1.186, okay? Now what I need to do is this. So think about a table. I said, find 3.2, find the log. Find 4.8, find the log. I add them together, I get that. Now what I'm doing is this. I'm not going to find the log of 1.186. I'm going to find 1.186 in my table part and go backwards. So I'm basically going to find 10 to the 1.186. Again, I don't have a calculator. So when I do that, guess what I get? I get that. Okay? Now, why is that true? Let's think about it. So what I'm claiming is that A times B, which is that, is equal to 10. What's that number? It's these two added together, right? 10, and what's that? Log of A, log B. So I'm claiming that AB equals 10 to the log A plus log B. Wait a second. Properties of exponents, now they didn't have all this stuff, systematized like we do. But that's 10 log A times 10 log B, isn't it? You add exponents when you multiply those guys. So AB equals, did I say that right? Yeah, that's fine. So AB equals, when you take 10 and you raise it to the log that is a base 10 of A, you get A. These are just inverse operations, 10 to the something, and log base 10 inverse. That's A, and that's B, boom. So it worked. That's how they, transfer it. Now we would never do that because we have algorithms, but that's how they would use logarithms. So there's some really cool stuff on logarithms. I'll probably look at it, a couple of them in problems. Let's see who's next guy. And then William Offred, he actually invented the slide rule, which you've probably heard of a slide rule, but it actually used logarithms to multiply numbers by adding. So you would, if you wanted to multiply, I mean, it did a lot of other things too. It developed over the years, but what it initially did was it was your calculator to multiply numbers. How did it multiply? Well, it did it by using a logarithmic scale, which gave you two numbers to add, and then you just take those two numbers and add them together. Well, I'll show you up here. You take those two numbers and you add them together, and there would be the answer. So that device there was used until the calculators. I mean, it was slowly improved and could do more. I mean, you could do trig stuff with the slide and so on and so forth. But he gave us a lot of symbols. Only a couple have survived, though. He's the one that, so if a student asks you, where's the x come from? Why do we use x for multiplication? William Offred, he used that for proportions. And we'll stop there. So for homework, well, actually, I guess I'd probably say, first, in closing, in closing, just think about where we are in history. We're now examining what led to the invention or discovery of the calculus. And I think this might be the most important thing to remember. It wasn't like calculus was just all of a sudden conceptualized by Newton and Leibniz. A lot of people led up to its discovery. So that's kind of where we are headed. And in fact, in the notes, I want you to go back over the overview, but then I also want you to carefully read through. I'll probably make a few points on Thursday, but depending on how I feel and get work done tomorrow, I'm hoping to have some other problems there for us to look at too. But look through that, we'll talk a little bit about, what various people did and, kind of see, those mathematicians end Newton and Leibniz, so you kind of see the progression, hopefully, of what various people did, so. All right. Well, I'm fine. It's just cold. I don't get the flu. It stays away from me.
No, I wasn't talking until I came here.
Yeah.
I have bronchitis back in November and didn't get rid of it until mid-February.
Oh, really?
Yeah.
That's not real. Yeah. Well.
Well, I'll email you on it.
One more class.
I just remember there was something on, hey Gary. What did we have to do for something? Was it just that one problem?
That one problem we did.
But wasn't there another one on the board before that she had written on the far board and she put something for?
Well, some of it was page 88. That's all I had written down.
That's all I noticed.
Paper. Yeah, that's all that
I just remember before we did that, there was something on the board on the far side that she put over. I could maybe take a picture. I think it was just
That's all I had written down.
Thanks.
Well, I started. What's up? I'm joining you this morning. All right.
I'm gonna miss it. Are you?
Yeah, she did. I think, well, no, I don't know if actually she should have done it, but I don't think she started it till last night. Seems like Ashley. Yeah. Well, that's nice. Yeah, probably. Give her like for reminders. So yeah. yeah, because at the end of these classes it's closed.
I mean, I took snacks to work today, but I ended up eating them all, and I'm still hungry.
You didn't take it up then?
I don't know, I haven't had so much. And then I had a granola bar, and then another granola bar. So,
I guess it wasn't.
and I had cereal this morning for breakfast. I'm already shocked myself. And then I had 2 cookies. So, I'm so hungry. I accidentally hit the panic button on my car.
Oh, good job.
So, oh shit, that's me.
At first you're probably like, man, what an idiot. Then you're like, shit, that's me.
There was like, there's someone coming.
See, I don't even know what my car sounds like when I press. I've never like actually done
I've never done it either, so I figured it's like if I were to push the lock.
I'll start going off and I'll be like, oh,
That's
that's mine. I've never heard that before.
So I had all my stuff done for my portfolio. I just have to put in my, what's it called, the GD test number 1. And then, I tried starting the homework on learning algebra. That's so fucking hard. Like the first like 7 or 8 problems are terrible. You don't have anything to really compare it to in the previous examples. So I might just start with the whole linear dependence and independence section. It's
Doesn't make me feel any better.
no. I tried to say.
I need to make my reference sheet still for that.
Yeah, I have to do
so.
that. I have to do that right tonight.
I'll probably do it tomorrow because I have to double check. And we don't have anything else going on this week. Other than like the assignment for this, of course.
And I wanted to skip Friday for so I clean the apartment, but we have the exam.
Oh yeah, you said that. Wait, was it this Friday or next Friday that you said that you were probably gonna take off and just go to one back?
Well, I was thinking about it this Friday, but then I realized we have that linear exam, so I'll probably do next Friday. I'll just go to the music because I have an exam for music next Friday.
Okay. Yeah, I think that's what you said. Yeah, I won't be here part of Tuesday. I don't know if I'm gonna leave after this class on Tuesday or if I'm gonna leave after spec. It just depends on what time we made the permit, which it'll probably be early. Cause he never knows when he gets off, so. Sometimes it could be 7 o'clock, sometimes it can be 4 o'clock. Just one.
More times this thing on.
It's at 11 in the morning, that's why we're leaving Tuesday night. We have a hotel tonight.
Nice.
Be there
In a hotel.
Woohoo! No, I'm already asleep.
Free continental breakfast.
Well, because we stayed there the last time that I went to Philly, so we got like the same hotel, which is nice.
Then we can figure out something. Are you waiting for me? Oh, okay, alright. Yeah, sorry. Oh, man.
Don't rush. It's okay.
No, I'm not. I totally forgot to shut this off from last.